Point straight down. Go ahead. Point to the ground beneath your feet. Now, imagine someone on the exact opposite side of Earth doing the same thing. They're pointing in the opposite direction. And they're calling it down, too. So, which one of you is right? Both of you are. And that's the first crack in how we think about space. Because down doesn't exist the way we think it does. Not beyond Earth, not beyond gravity. And once we leave Earth behind, the structure of our entire solar system becomes stranger than we were taught. For decades, astronomy textbooks showed us something simple. A flat solar system, a thin disk, the planets orbiting the Sun along a narrow plane called the ecliptic. Mercury, Venus, Earth, Mars, all lined up like grooves on a vinyl record. Everything moving in nearly the same direction, clean, organized, predictable. And naturally, if everything is flat, then above and below that plane should be mostly empty. Right? That's what we assumed, until we actually reached the edge. In 2012, a spacecraft did something no human-made object had ever done before. Voyager 1 crossed the boundary of the Sun's influence, about 11 billion miles from home. Its instruments detected something dramatic. The solar wind vanished. Cosmic radiation spiked. Plasma density jumped nearly 40 times higher. It had crossed the heliopause, the edge of the Sun's protective bubble. But here's what no one expected. The boundary wasn't where we thought it would be, and it wasn't shaped the way physics predicted. For years, scientists believed the heliosphere looked like a comet, rounded at the front, with a long tail streaming behind it as the Sun moved through interstellar space. That model made sense. It was neat. It was elegant. It was wrong. When researchers rebuilt the heliosphere model using real data from multiple spacecraft, they found something bizarre. The Sun's protective bubble isn't comet-shaped. It's warped, compressed, bent inward, more like a distorted crescent than a streaming tail. Interstellar magnetic fields were squeezing it. Galactic pressures were twisting it. Forces we underestimated were reshaping the boundary itself. And it gets stranger. Voyager 1 and Voyager 2 crossed this boundary at nearly the same distance from the Sun, but from different angles, and they measured different plasma densities, different magnetic conditions. The edge changes depending on where you cross it. There is no clean, symmetrical border. The first layer of our solar system isn't stable. It's dynamic, uneven, alive with pressure from outside. And that's only the beginning. Far beyond the heliosphere lies something even larger, the Oort Cloud, a vast spherical shell of icy objects, not a disk, not flat, a sphere, surrounding the Sun in every direction, above the planets, below them, sideways, everywhere. It may stretch from 2,000 astronomical units to 100,000, nearly halfway to the nearest star. Here's the unsettling part. We've never directly seen it. Not one confirmed object. Every telescope humanity has built cannot detect it unless one of its objects falls inward and becomes a comet. And yet we know it's there. Because long-period comets keep arriving from every direction, tilted at extreme angles. Some moving backward compared to the planets. They don't come from the flat disk. They come from a sphere. Something out there is sending them inward. Recent models suggest the Oort Cloud isn't even uniform. It may have internal structure, density variations, regions shaped not just by the Sun, but by the Milky Way itself. Over billions of years, the gravity of our galaxy exerts tidal forces on this distant shell. Subtle pulls, slow distortions, occasionally dislodging objects, sending them screaming toward the inner solar system. That means the true outer boundary of our solar system isn't defined by the sun alone, it's shaped by the galaxy. We are embedded in something larger, and that changes everything. Now consider this. The flat plane where all the planets orbit, the ecliptic, is tilted about 60 degrees relative to the plane of the Milky Way. So, when you travel up from Earth, you are not leaving the galaxy. You are cutting diagonally through its disk, through regions filled with stars, nebulae, molecular clouds. Up doesn't mean empty. It means dense. It means structured. It means crowded with cosmic architecture. And if the cloud of gas that formed our solar system had rotated differently 4.6 billion years ago, up would point somewhere else entirely. Other stars, other constellations, other regions of the galaxy. There is no universal vertical. Every solar system defines its own. Every galaxy defines its own plane. Direction is local, not cosmic. Voyager 1 will not reach the inner edge of the Oort Cloud for centuries. Crossing it completely could take tens of thousands of years, and during that entire journey, it will still be inside the solar system, because the solar system doesn't end at the last planet. It doesn't end at the heliopause. It ends where the sun's gravity finally loses to the Milky Way's pull, possibly 1 to 3 light years away, a boundary we cannot see, a border we cannot image, an edge that exists only in equations. Beyond it, other stars, other solar systems, possibly other Oort clouds overlapping with ours, interstellar gas streams, magnetic fields threading through everything. There is no sharp line. There is no clean divide. There are only gradients, layers, regions where one influence slowly gives way to another. So what exists above and below our solar system? Not emptiness, structure, forces, nested spheres embedded within a galaxy that is itself embedded in something larger. The more precisely we measure the universe, the less simple it becomes. The edges blur, the shapes warp, the directions dissolve, and the further we look, the more we realize that up and down were never fundamental at all. They were just conveniences, created by gravity, on a small planet, orbiting an ordinary star, inside a structure far larger than we ever imagined. If you enjoy exploring questions that only get bigger the deeper you go, there's a lot more out there, and we're just getting started.